Alright, chapter 14, we're going to be dealing with acids and bases, and more specifically, some of our weak acids. Now, something we did in the past when we introduced acids is we actually never really talked a lot about how you could tell the difference in the strengths of our weak acids. Acetic acid versus citric acid, we would have known they were weak acids, but if I were to ask which one was a stronger acid, or even to calculate the pH of one, that was something we left out. Now, there was a reason for that. And it actually has to do with how they behave. Alright, in the past when we talked about a strong acid, we did say the biggest difference between a strong acid and a weak acid was how much they disassociated. All strong acids basically totally fall apart. Any strong acid that gets in there, there's pretty much none left. It's all turned into, well, that should be H3O and A-. Yet a weak acid doesn't do that. It has an equilibrium going on. I left the 3 out there too. Alright, but that's the difference. Now, technically, now that we've actually covered equilibrium, we're starting to start to realize this is an equilibrium. That's what's going on. The reaction, when it's all done, there is, yes, definitely some H3O made, but there's still quite a bit of HA, the intact source of the H's. That acid's still intact. So we're going to have to add to our understanding of equilibriums to understand what's going on with our strong and weak acids. Alright, so it's going to help us explain what's going on here. So this is a typical single replacement reaction where we take zinc and we treat it with acid and you get some hydrogen gas coming off. And if we do that with HCl, we get very vigorous reaction. Yet if we do vinegar, it does actually react. It's just really, really slow by comparison. But this is going to be related just to the strength of the acid. Technically, HCl, even though they're both 1 molar, this is a stronger acid because there's more H pluses actually available. Over here, this stays mostly intact and only a small amount got turned into H pluses. And that small amount was just too little to get that reaction going. Alright, so let's start by actually figuring out if we can tell what a reaction dissociation constant looks like. Alright, so it doesn't matter what the equation is, whether it's a strong acid or a weak acid. We do have a K for that. It would be the H3O plus. There we have it with H3O. A-, and then on the bottom is HA and water. And all acids would look like that. That's our acid. There's the conjugate base of the acid. The weird thing is, these will always be done in water. Water, for the most part, is going to have a constant concentration because it's not really affected by these. It's going to go away. So we're going to see more often than not a Ka for acids that has just the H3O and just the A- on top, just like before, but on the bottom is just the HA. And we don't really worry about the water. Now, on a strong acid, even though we say, and we still draw it with a one-way arrow, it doesn't mean it totally goes there. That's just never going to go to 0. It just goes really, 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 really small. Because the K's for our strong acids are very, very large. K's for weak acids are just less than 1, really, and they still have both existence. And here are some various different K's for some of our so-called weak acids. Alright, now, I say so-called because some of these are pretty nasty. I mean, that could actually kill you, even though it's a low concentration, especially if it comes out as a gas. But we have a lot of different ones, and according to this, at least as an acid, chlorous acid is our strongest one because it has the largest Ka. Alright, but now that we have Ks, we can see that's what we're going to use to help calculate the pH of a weak acid. Alright, so let's actually clarify some things though. In the past, we actually talked about strong acids, and we did list these 6 right here as the only strong acids. Well, that's not entirely true. There are other strong acids. These are just the 6 common strong acids. Matter of fact, there's plenty of acids made with polyatomic ions. As long as we have at least 2 more oxygens than protonatable hydrogens, it is going to be a strong acid. And there is an actual stronger acid than sulfuric acid. It actually has another oxygen on it. It's a pretty nasty stuff. They typically make it when they need it. And there have been explosions based on it because not only is it a very strong acid, it's actually kind of unstable. All of our weak acids just have an H somewhere they can come off. And our organic acids, somewhere in the molecule, they have COOH. They are abundant all over. All your amino acids are they have those in them. So every bit of your proteins in your body and anything that you've eaten actually are acids, at least weak acids. Alright, strong bases are still the same thing, weak bases are still the same. We're not really changing anything at all from that definition that we introduced in general chemistry and even intro. So our strong bases are anything that has an OH that's easily soluble, like group 1s. And our weak bases are ones that don't dissolve easily, or things that contain nitrogen, where the nitrogen has a lone pair on it. So all these, the nitrogen has a lone pair. As long as it has a lone pair, it is actually a base. Alright, so let's see if we can figure out what these are. Alright, that first one has H's there. Would we assume that's a strong acid even though it's got Se? Well, number of oxygens is 4. Number of hydrogens we're applying that come off is 2. That's more than 2. We would actually call that a strong acid. Next one has that COOH. That is definitely a weak acid. KOH is K one of our supersoluble bases. Yep, strong base. And there's a nitrogen with 3 things on it, so that is a weak base. Alright, next thing we're going to talk about, since we're actually going to restrict these to water, we got to talk about the fact that water by itself forms ions just by them bumping into each other. So when 2 water molecules bump in, there is a chance the hydrogens exchange. And these guys will be attracted to each other, so they will actually combine and go backwards. Now this does happen a small amount of time. At 25 degrees Celsius, this is going to be roughly about 55 molar, but this is about 1 times 10 to the negative 7th molar, and so is this in neutral water. Now that 7 should seem somewhat weird, because if you ever think about it, pH of neutral water is a pH of 7. That's where that comes from. That always happens in neutral water, that they actually exist. Matter of fact, it's such a repeatable process that we actually can turn that into a K. And if we plug those in at that 1 times 10 to the negative 7th and 1 times 10 to the negative 7th, we see that this equation is always equal to 1 times 10 to the negative 14th. We can use that anytime we want to figure out what the OH concentration is if we're given the H3O concentration. They are always going to be mathematically comparable to that 1 times 10 to the negative 14th. Even to the point where we actually can do some cool little math on it. So here's something we're going to do. We're going to look at HCl, a strong acid, and we say we've actually tested it and we got an H3O concentration of 3 times 10 to the negative 4th. We want to know what the OH concentration is, and then is it acidic, basic, or neutral? Alright, to solve for this, we have that Kw equals H3O plus times OH minus. Kw is just always 1 times 10 to the negative 14th. The H3O is given as 3.0 times 10 to the negative 4th. We're just going to solve for the OH concentration. Fire up my calculator. 1 times 10 to the negative 14th divided by 3 times 10 to the negative 4th. We get 3.3 times 10 to the negative 11th. And now, is it acidic, basic, or neutral? This is a bigger number. It's acidic. Technically, we could have done that right off the bat. Since that value right there is a number that is bigger than 1 times 10 to the negative 7th. That's the middle range. Since that one's bigger than it, it's definitely acidic. Alright, pH scale is used to get rid of those exponents. And all we do to get the pH is we just take that number that we just got, or we had 3 times 10 to the negative 14th, or 3 times 10 to the negative 4th. And if I wanted to get the pH of it, I just take the log of that and then flip the sign that it comes out with. So the pH of that 3 times 10 to the negative 4th H3O concentration is 3.52. And technically, if you ever want to figure out the H3O concentration and you're given the pH, you're just going to do 10 to the negative of the pH. In this page, we just give you various different things that you might come across that have a pH. And everything that has a variety to it is listed there. Even our tap water, not really on here, because you find that most city tap water It does vary quite a bit day to day, and even how long it's been running, because water sitting in your line typically will change its pH based on how it reacts with the lines. And then once you get it flowing, it will actually change. All right, various different things. I want to introduce this weird thing. We got something called a POH. Well, POH is determined from the negative log of the OH. That little P just does mean take the negative log of it. And we have another neat thing. If you have the pH and the POH, they will always add up to be 14. All right, how could we apply that? We see something interesting pop up in some of our later chemistry classes. Rather than list Kas, you'll see them list pKas. pKas are always going to be nice little whole numbers that have taken essentially that exponent and turned it into a nice whole number or close to it. They did the same exact thing. To get a pKa, they took the negative log of the Ka. Alright, let's do some weird stuff with another strong acid. I've given you a bunch of different concentrations of the HNO3. Turns out that, being a strong acid, is technically also the concentration of H3O. So I'm just going to write these down. And we want to actually do some things with it. We want to calculate the pH from each of these, the OH from each of these, and the POH. Now, the pH is probably the easiest one to calculate right off the bat because I'm just going to do the log of whatever that number is. So pH here is negative 0.30. pH here is 0.52. And pH here is 2.20. Now this is something interesting. See how this has two significant figures and it looks like I put 3 here? Turns out on a pH scale, the leading number, no matter if it's there or not, is never significant because that's more like the exponent. The significant digits on a pH scale are actually the decimal places. Alright, if I have that, it's easy to get my pH because these two add up to 14. So this is going to be 14.3, this is going to be 13.48, and this is going to be 11.80. Because I need those two numbers to add up to 14. Alright, now I have two different ways I could calculate the OH. I could take the 2 and do the 1 times 10 to the negative 14th divided by the H3O concentration, and I get that this is 5 times 10 to the negative 15th. But another way I could have done it and got the exact same number was take that POH and did the inverse log of negative 14.3. I get the exact same number or thereabouts. So, let's see, 1 times 10 to the negative 14th divided by 0.3, I get 3 times 10 to the negative 14th. And then the last one, 1 times 10 to the negative 14th divided by 0.00663, I get 1.6 times 10 to the negative 12th. These are all molarity. pH doesn't really have a unit. Okay. pHs are typically obtained two easy ways in a chemistry lab. The pH paper is probably the go-to easiest way, but these aren't super accurate. Remember we're talking about significant figures? You could probably tell sometimes if it's between a color. You're adding one significant figure at best because the whole number that you're estimating based on the color isn't actually telling you anything other than the power or the exponent. We typically use paper indicator to tell if it's acidic enough or basic enough, or if you've spilt something, I use it as a way to know if I should clean it up with just a paper towel or gloves. If I want more accurate numbers, I use an actual pH meter. These are getting a little bit more common in chem labs because they're getting cheaper and they're easier to interface and they're borderline more durable. You actually can get pH probes now that are metal probes that you just leave in the ground. So they actually have them that they leave in the greenhouses to measure the pH of soil, and they don't have to worry about actually doing much of anything. They're very, very stable. Okay. Backing up a bit to a definition of an acid. In the early days of adding acids, we talked about how they produced H's and bases were ones that produce OH's. Well, for the sake of our weak acids and weak bases, we're going to talk about the transfer of just protons. We're going to use the Bronsted-Lowry definition of an acid. So Bronsted-Lowry definition basically says an acid is a proton donor and a base is a proton acceptor. Now in these two examples here, I have water acting as a base and accepting a proton, and water acting as an acid and donating a proton. Water can do both. But in this case, I have it compared with something that is definitely an acid, HCl. HCl is going to definitely donate that, become Cl minus and H3O. NH3, being a base, is going to accept that proton, become NH4 positive and OH. So that's what we're showing. That's what the arrow is supposed to be representing, just how the H moves. Now, what's interesting is my arrow is actually backwards. Typically, we show the, oh no, I take that back. It is actually right. The lone pair is what attacks. The lone pair is what attacks the H. Okay. Now, the neat thing is about the Bronsted-Lowry definition, it can be used to explain any of the acid-base properties that we're going to see. So we're just going to actually study where that proton moves and how it moves and what it moves to. And we're going to say this creates conjugated pairs. So those conjugated pairs are just the species that had the H and then what it turned into when the H left. So like on that previous one, we had H2O accepting an H and becoming H3O plus. That is a pair because the only difference between those two is a single hydrogen and a positive charge. Let's look at some more examples of this. So I have a bunch of acid-base reactions here. I got 7 actually. And what we're showing is what happens if we treat the thing in the first row as an acid and the second one as a base. Or second one as a base. So this donates the H to that, making an H3O. Leaving behind just an F minus. And that does mean that this is a conjugate pair to that base, and this base is a conjugate pair to that acid. And it works like that all the way down. The acid here donates an H there, so it's left with the COO minus, and this is an HCN. Now, I actually repeated a reaction 4 when I made reaction 7. The reason I did that is I wanted to actually show you something that's kind of interesting that some acids can have. Alright, I want you to notice that technically both these species have H's. Both of them could act as the donor. So let's say we want this to act like the acid and this to be the base. Now if it was like it's written, it just comes out here. The H goes over to make water. But if we're going to have this act as the acid, the base it turns into is O2 minus. It loses that H. And that H ends up over here and makes H3PO4. That still fits this category. It is actually just showing the OH acting like an acid. Now there is a reason it doesn't. We are going to talk about the strengths of acids here in just a second. And we could actually always tell which way it's going if we pay attention to what's going on. Now sometimes it has to go a certain way. Like that guy right there could never act like an acid because it doesn't have any H's on it. But when you have species that have, both of them have H's, like reaction 6 does that, then you actually have to consider which one is going to act like the acid. Alright, let's do some more with these. Alright, let's see if we can figure out what the pairs are here. And then we're going to take this a step further and see if we can figure out which direction the reaction seems to go. Alright, so first one. What is the conjugate pair of H2PO4? Well, it must be just the HPO4 2 minus. And the pair with the CO3 is the HCO3. The water is paired up with OH, and the SO3 is paired up with HSO3. So those are the conjugate pairs. Now let's see if we can figure out which is acting like the acid and base all the time. Well, weird thing is, this looks like we want to find the acid and base on both sides. You will find it's much easier to identify on the pairs which one's the acid and the base. Because, think about this, I have H2PO4 versus HPO4. This has more H's. Even here, HCO3 versus just CO3, more H's. And you can always do that. More H's, more H's. It'll always work that way. When you look at the conjugate pairs, the one with more H's is the acid, the one with less is the base. And it never fails to work out. Now here's something neat. We can actually take this, see how this is going to want to know if the K is big or small. We want to know which direction the reaction's going. We can actually call that in some cases. So here's what I mean by that. Let's think about the strength of these two acids. Can you tell which one's the weaker of the two? Well, yeah, because water, by far, neutral thing, is the weakest weak acid there is. So that is definitely a weak acid. This, therefore, must be the strong acid of these two. And because of that, this is strong and this is weak. So the strongs are always together. Because of that, because we can actually make that call, because this is water, we know this reaction is going to tend to go backwards. They go away from the strong side. So we can actually kind of say that this K is small. It favors going backwards. Let's see if we can do that on these two. These are slightly different. The bottom one is a similar property because it's got water, but the top one's not. So let's see if we can figure out which one's the acid and base, and then figure out if we can tell which direction it's going to go. All right, so my first pair is H2PO4 and HPO4. This must be the acid, that must be the base. And the other pair, NH3 and NH4, this is the acid, that's the base. All right, our two acids are NH4 plus and H2PO4. I don't know anything at all about those two to know which one's stronger than the other. Neither one's a strong acid, neither one of them is water, so I can't make an easy call. So let's look at the bases. Do we know anything about that? Well, I know NH3 is a weak base. I don't know anything at all about that. It's probably a weak base. Can't make a call on this one yet because we don't have any outliers or any rules. We can definitely make a call down here because I see water, and I know that's the acid and this is the base. This must be the weak acid because water is always the weak acid or the weak base. This is going to be an acid, this is going to be a base. These must both be the weak, this must both be the strong. It's going backwards. Now the reason I always know water is the weak acid is if I were to rank all of our acids and bases, water is the weakest weak acid. It's also the weakest weak base. So whenever we have water, regardless if it's an acid or a base, it's going to be weak. And then the rest get ranked based off that. They're based on those Ka's. Well, to do that first one, these acids, we need a chart like this. Because look at this. We got H2PO4 minus, which is H2PO4 minus right there. And we wanted to compare that acid with NH4 as an acid, which is right there. And just because of this chart, now we know that's the strong one, that's the weak one. And if we had done it with the bases instead, we see the same type of thing, because there's the NH3, there's the H2PO4 minus, and NH3 is the strong base. Once we have that, we can tell strong is going to go forward, this is a large K, and this one going to go backwards, it's a small K. But the only way we can do either one of those on the only way we can do this is if I use water or a strong acid, or if I give you a chart like this. Okay, let's do a little bit more with this. I'm going to give you an actual acid and ask you to determine the pH given the concentration. Oh no, I take that back. I gave you the pH. I want to know what the Ka is. Alright. I'm actually going to simplify this. I'm actually not going to simplify it as HPAC. I'm going to simplify it as HA. All weak acids bump into water and make A- and H3O. And this is implying my initial concentration. Now you remember how when we first introduced Kas, we talked about ignoring the water? I'm actually going to ignore it from the get-go in these tables. And since we're talking about initial concentrations, wouldn't we assume from this read that there's not been any of this A- added, so we're going to assume this is 0. Matter of fact, we would have, in the last chapter when we introduced equilibrium, said this is 0. It's not really though, because wouldn't it be safe to imply that we used neutral water to begin with? Yeah. So this had a small amount to begin with because of that. So I can't put 0. But it still actually has a very predictable direction. That must go up, therefore this goes up and this goes down. So equilibrium, this is 0.12 minus x, this is x, this is 1.0 times 10 to the negative 7th plus x. Now in this case we can figure out what x is because I gave you the pH. So we could say this, 10 to the negative 2.62 is equal to this 1 times 10 to the negative 7th plus x. Let's use that to solve for x. 10 to the negative 2.62, very small number. I'm going to subtract this from it, minus 1 times 10 to the negative 7th. Look how little difference it makes. It's way out here, insignificant digits, right? We're going to see most of the time we can ignore that x. Or not the x, we can ignore the 1 times 10 to the negative 7th. And we could have done that here and it wouldn't have made a difference. Well, that's our x, 0.002398. Alright, we're going to essentially plug that into this. So our Ka is going to be that x times, I'm just going to say it's x again because we know it's close. It's going to have a small little error. And then we're going to just do 0.212 minus the x. So all I'm going to do to get this math, with that number in my calculator, I'm going to square it. So take the answer and square it, because that's x and x. And then I'm going to divide that by 0.12 minus our x again. And we get a Ka of 4.89 times 10 to the negative 5th. Alright, I want you to notice something though. I'm going to bring back up this calculator. See how small that x value was? Would that have made a difference here? Not really. Here's the neat thing we could have done. I actually could have done this instead. Just taken that 2.62 and got the pH from it. 10 to the negative 2.62. I know that's roughly x, and that's why it's duplicated here, so I'm just going to take that number and square it. And then, to get this number, I'm just going to divide by the 0.12. I'm not going to subtract the x at all. Look how close to the same answer it is. Most of the time, if I want to get the pH of a weak acid, I can take this equation here and say instead it's kind of like the H3O concentration squared all over whatever the initial concentration of the HA is. And I don't have to do this full table. Now the nice thing about doing the full table is it catches any mistakes we might make. So I typically do the full table. It's just that we can always make assumptions on it. Let's do another one of these. No assumptions whatsoever. We're going to figure it all out. So I got propanoic acid, and I want to know what its H3O concentration of a 0.1 molar solution it is. So I'm going to simplify this as HA. and I'm going to say initially this is 0.1 molar. I'm ignoring this. This is 1 times 10 to the -7th, and this is 0. Therefore, this goes up, and that goes down on my change. So at equilibrium, this is 0.10 minus x. This is 1.0 times 10 to the -7th plus x, and this is x. Now we have 1.3 times 10 to the -5th should be equal to 1.0 times 10 to the -7th plus x and x all over 0.1 minus x. Theoretically, I can throw that into my calculator, my graphing calculator, and just solve it like it is. So I'm going to do that so you can see what this answer is, and then we're going to make an assumption on it. You're going to see the assumption doesn't really lose anything at all. So there's the 1 times 10 to the -7th plus x. We have another x. Oh. Sometimes you actually need to tell it to multiply these. It doesn't always do it quite right. At least this calculator doesn't. And then minus 1.3 times 10 to the -5th. And graph it. And then calculate a 0 that's somewhere between 0 and 0.1. And I get an x of 0.00113. Alright, that's the correct, perfect answer, and we could use that to calculate the H3O. And then, if that is the case, to get our H3O, we're just going to take that x and we're going to add the 1 times 10 to the -7th to it. So, 0.00113 plus 1 times 10 to the -7th. Yeah, see how little it changed? The x is, the hydronium concentration is 0.00113 molar. Okay, let's pretend that we knew ahead of time this x was really large compared to this, and it was small compared to this. So what we're going to solve instead is just x and x here. Ignore this totally, and down here is just 0.1. It makes the math a heck of a lot simpler, doesn't it? Well, let's see what it actually does to our math. So 1.3 times 10 to the -5th times 0.1, and then take the square root of this. Get pretty much the same number. Well, turns out we can always do this on weak acids. In equilibriums, we had to check assumptions. And weak acids don't really need to most of the time. If it's actually something that is a weak acid and has that small k and has a relatively high concentration of acid, the assumption's always going to work. So you can always assume that is marginal and ignorable, and you can always assume it's ignorable over here. Alright, introducing a small problem here. Some acids have 2 protons that come off. Oxalic acid, for instance, this H comes off easily, or that one, but as soon as one of those 2 H's comes off, the whole molecule holds onto the other H higher. So you have a K that represents when one of those H's come off, and you have a second K for when the other one comes off. And then if you look, we got multiples of these that have more than one H that comes off. Alright, my question is, how's that going to affect our pH? So let's look at ascorbic acid, vitamin C. And we're going to see how we would do this math, and we're going to make some odd assumptions. Alright, so what we're going to do, instead of HA, I'm going to do H2A. I'm going to let it bump into water and create some HA minus and some H3O plus. And it says right here our initial concentration is very low, 0.00 or 0.50. I can still ignore this because we're dealing with Kas, and we're going to assume this is 0, and we're going to assume this is 1 times 10 to the negative 7th. And our change still looks the same. Since that was 0, these two go up, and this goes down. Alright, now before we do any calculations or any assumptions, let's take this HA, the HA minus now, let it bump into a second water, and create the A2 minus, and some more H3O plus. Now the reason we have to do this is because this has both K's. The first equation is dependent on the second one because these, the HA minuses, are those reactive intermediates. Alright. Let's see what we got here. This started out as 0, now it's X. I can still ignore this. My A2 minus here must be 0, but the H3O is 1.0 times 10 to the negative 7th plus X. It's this. We've just brought it down. Now, change here, I can't use X because I use it up here. I'm going to use a Y variable here. I'm going to say this goes up because it was 0 before, therefore this goes up, and this goes down. So this is X minus Y. This is just Y, and this is 1.0 times 10 to the negative 7th plus X plus Y. Okay, let's put our K's together with from our Q's. So this first K, 1.0 times 10 to the negative 5th, would be equal to X times 1.0 times 10 to the negative 7th plus X. And down here is 0.050 minus X. And then our second K, 5 times 10 to the negative 12th equals Y times 1.0 times 10 to the negative 7th plus X plus Y all over X minus Y. Now, if we're in a math class, we could have a field day solving this the right way, where we'd actually have to solve these two equations simultaneously, and it would be very time-consuming. We're going to make some assumptions, and they are based on the fact that this being very small, this reaction doesn't go very far forward. So how big is our X? Is it going to be enough to affect this? Probably not. So we're actually going to solve it by ignoring it. We're also going to ignore that 1 because we're going to assume it's very, very large. And just for kicks, let's solve for what that X is and see if that seems to be a sensible reaction, or if that seems appropriate. So 1 times 10 to the negative 5th, I'm going to multiply it by 0.05, and then take the square root of that. And that gives me an X of 7.1 times 10 to the negative 4th. Alright, is that small compared to this? Definitely. Is that large compared to this? Definitely. Our assumption is safe on this weak acid. That is a very safe assumption, and that is also what we're going to say is the HA minus concentration, because that's the only thing that's dependent on. And technically, if I did any math here, I would actually see that the H2A pretty much still sticks right at 0.050, because 0.050 minus 0.0007, we could maybe say it's 0.049. Why don't I do that? That's a little bit more accurate, isn't it? But it doesn't change much because this wasn't a very big number. Alright, let's see if that helps clear this up. Alright, rather than actually plug in that X and do anything with it, let's think about what the size of this Y is. And you see how small this number is? This reaction doesn't go forward hardly at all, does it? So is the Y going to be a very big number? Probably not. Now I can't ignore it here because it's the only thing that makes up this value. But I can probably ignore it on these two. So I am. And you know what? Remember how we ignored this before? Still am. So this is X and X. I'm ignoring everything. The A2 minus concentration is just the second K. It's a very, very, very small amount. But the only way to solve these the right way is to spend a lot of time with your calculator. We always do assumption when we have diprotics. And the biggest reason we can do that is the first reaction is the one that creates all the chemistry, all the acid. The second reaction doesn't really add anything to it. It just tells us where all the conjugate base ends up. So if I'm in a chemistry lab and I need to quickly calculate the pH of a diprotic weak acid, I'm actually just doing that first calculation and figuring out what the H3O is. The other two don't really affect the pH that much, but the first one definitely creates all the acid that you're going to see. Alright, this talks about bases. Turns out there are weak bases. They use an equation called Kb. And Kb looks something like this. And technically what this means is we have a base, bumps into water, and the base accepts the proton, becomes Hb positive, and leaves behind some OH. And this is just a manipulation of that to give it that way. Now, sometimes what we actually see to get a common notation is we actually see this called HA, and this is the A minus. Because it's what's really interesting. Our conjugate bases of our weak acids are also weak bases. So they're actually interchangeable. They go back and forth. All right. We've already seen. Let's actually, and I just divide that. Let's look at how this affects an actual calculation. All right. So I have a weak base, dimethylamine, and I have a Kb of it, and I just want to calculate the pH of a 1.5 molar solution. Rather than write this out, I'm just going to say base. Bumps into water, gives Hb plus and OH minus. We're doing an ice table. This is 1.5. We can ignore water for the same reason we've ignored them on the acids. This is 0, and this is 1.0 times 10 to the negative 7th. Because it's neutral water. So this must go down to make that stuff go up, therefore this go up. We have 1.5 minus x, and 1.0 times 10 to the negative 7th plus x. You notice something though? Doesn't this look familiar to what we've been doing? This is a reasonably small number. So rather than actually write out this full math, I'm going to write out what I'm going to do as an assumption. I'm going to assume this is x, and that is too insignificant to count, so I'm dropping the 1 times 10 to the negative 7th. And I'm just going to divide this by 1.5 rather than 1.5 minus x. Let's see what our x comes out to be. 5.9 times 10 to the negative 4th times 1.5, and then we get the square root of that. And I got an x of 0.0298. Alright, now it wants the pH. If I do the negative log of that, why am I not getting the pH? Well, because that is our x, which is the OH concentration. This is a POH. So to get a pH, I'm getting the difference between that and 14. So pH of this base, 12.47. I think that's what that said. Yeah, 12.47. All right. Got something interesting that pops up. At this point in your book, it talks about how you can relate Ka to Kb. As a matter of fact, it says if you're given one and you need the other, they always multiply together and give you Kw. All right, that is going to be true in this class, but I'm introducing how that comes about so I can explain where it fails, because it doesn't always work out that way. It just does on simple acids and simple bases. All right, so you notice how this is just our acid equation? Well, that gives us a Ka, which is H3O and A minus all over HA. Now, technically this is a base equation, but rather than say base, turning into HB plus, we said A minus turns into HA. We did that so we could actually get an equation that has the same two components in there, as in the HA and the A minus in both species, or both equations. Because look at this. If I were to somehow multiply Ka times Kb, if I multiply these two together, the H3O and OH would be in there, but the HAs would cancel and the A minus would cancel. That's what Kw is. So it turns out Ka times Kb definitely equals Kw. Now, I mentioned that I wanted to explain where it doesn't work. See, the reason it works is because all of the simple acids and simple bases we're working at, the HA and the A minus are interchangeable. But a sample where it's not, an amino acid, a very simple amino acid, the simplest one we have, glycine, has a COOH, has an acid. That doesn't look like an H. On the other end, it has an amine, a base. Amino acid. Alright, here's the interesting thing. There is a Ka that talks about how well that H comes off. The Kb for that is how well the H goes back on in that place. But it turns out there's a easier to get to place. This one down here has a Kb. So up here where Ka times Kb equals Kw, it really is talking about if the location where the H comes off and goes back on is the exact same location. On our more complex molecules, we have two different places where the H can, we have a place where the H can come off, and we can have a place where the H gets added to it, and they're not the same location. All right, you don't need to worry about that in this class. If I give you an equation and I say I want you to give me the Kb from a Ka, you are going to use this equation. It's always going to work. There are no exceptions in this class. The exceptions have to happen after Chem 2. All right, let's look at what I mean by that. That's sodium acetate, used to actually used as a base in this case. And I want to know what the pH of a 0.25 solution of it is. I gave you the Ka of it. All right, reason I did it this way. Rather than say NaAC, I'm going to actually list that as A minus, because that's why we use sodium. Sodium's a spectator most of the time. It goes away. That A minus, the acetate, bumps into water, takes an H away, and makes some OH minus. That's where this works as a base. When we have initial concentration of 0.25, we can ignore this. This is 0. This is 1.0 times 10 negative 7th. Our change, this all looks very similar, doesn't it? Yeah, because we're doing the same thing on all these for the most part. Oh, not 0. Now, we could set up a equation with a Kb that would have x and x over just 0.25, because we can do those assumptions. I didn't give you a Kb, I gave you a Ka. Gave you the Ka of acetic acid. So the very first thing we're going to do is get the Ka into, or turn the Ka into a Kb by using the Kw. And then we're going to solve for our x. So 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th. That should be our Kb. We're going to multiply that by 0.25 and then take the square root of this answer. I get an x of 1.17 times 10 to the negative 5th. This thing wants a pH, so I'll get the POH by doing this. POH is 4.93, and then I'll get the difference between that and 14. My pH is 9.07. Alright, what is next? Talking about first some strengths of acids in general. Now, what we have here is just our binary acids, where we take an H and put it with something on the periodic table. Now, I already know from previous rules that these guys down here are our strong acids, HCl, HBr, and HI. Now, the reason they are, turns out as you go down on the periodic table, this bond gets longer and therefore a little bit weaker. So our strength goes up because of the size of the nonmetal. So, increases with size. Left to right, though, what happens here, the reason HF is a stronger acid than H2O is because the fluorine, being more electronegative, pulls the electrons away. So left to right is due to electronegativity. Now, it can't be both, because technically if it was based totally on electronegativity, fluorine would be the strongest. And if it was based totally on size, beryllium would be, because it's the largest of these. So it's not both. It's up and down as size, left to right is electronegativity. All right. When we have our oxo acids, electronegativity does play in. What I mean by that, iodine, bromine, and chlorine. Chlorine is a little bit more acidic because the chlorine is more electronegative. When I have multiples on here, the oxygen pulls even more. So we get more electronegativity. I said that top thing backwards, didn't I? Yeah, so the electronegativity pulls away and actually makes this bond stronger. So on the top one, when we just have the halogens, I want the less electronegative thing to make it actually a weaker bond over here. Alright, next little weird thing. Turns out most of our highly charged metal ions also act as acids. Now, I have several of our highly charged metal ions, and I'm going to show you that the reason they act like acids has nothing at all to do with this. It's the fact that these guys organize waters around them. And like that top one there, the FeH2O6, the reason that stuff acts like an acid is because it can bump into water and make some H3O. It does that by taking one of those H's off one of those 6 waters. It ends up with 5 still intact, but one of them is now turned into an OH, and our charge went down by 1. All of these can do that, and all of these actually have 6 waters that they organize around them. And if you notice, the iron is a little bit more acidic than all the others, but all of these are slightly acidic. That's why those numbers are, that's why they have the Kas. Looking something like this, they actually do organize the water more like a Cartesian coordinates arrangement type thing, and we do just lose an H off one of those water molecules when it actually protonates. And it can diprotonate, so some of these have a Ka1 and a Ka2. Alright, next little thing we're looking at is trying to predict if an ionic compound is acidic or basic. Alright, so what I mean by that, I would like to know, how can I tell adding sodium chloride should not affect the pH whatsoever, based on the fact it's sodium and chlorine? Well, it turns out it's kind of actually based on what we know about strong acids and strong bases. So, looking at our 2 species, we have Na+, which would need to team up with the OHs in the water to neutralize itself, and the Cls would have to neutralize themselves with H's. Well, what do you know about NaOH? Well, it's a strong base, and because it's a strong base, it's never going to form. So, since all of these cations are the conjugates of strong bases, they don't do anything at all with water. They just float around, they stay spectators the entire time, so we can just ignore them. There are no way that those guys are going to affect the pH. And the same thing with our chlorine, bromine, and NO3. Those are the conjugates of strong acids, so we totally ignore those. So neither one of those species can do anything at all with the OHs or the H, so the water stays whatever it is. So pH is 7. Now, next category, we still have the strong bases, so we can ignore those right off the bat. There's no way they're going to do anything. But the rest are weak acids. NH4, for instance, could bump into water, and actually react. But we're not going to let it bump into water. We want to talk about the components in the water that make it neutral. The OHs are balanced out perfectly with the H's. The OHs can't be balanced out if we're adding all these NH4s. It's the conjugate of the cation of a weak base is going to take away some of the bases and make this slightly more acidic. On the next category, we can ignore the anions again, but now we have highly charged metals. Highly charged metals are slightly acidic, so we could actually write it as the Al with the 6 waters, and that 3 positive is also going to bump into OHs, take some of them away, and make it acidic. Now, we're going to skip this next section. There is a better way to look at it that works always, because there's exceptions to this. But this last one, we can actually do this. So, ignoring the cation, that is a strong base cation, we're looking at just the anion here. So we have CH3, COO minus, F minus, and CO3, 2 minus. Technically, those are conjugate bases of weak acids. So those guys getting in there can take away some of the H plus floating in there, which is why it's basic. Alright, our weird exception and some of the other ones we're going to cover next. Alright, let's see if we can actually predict some of these. So I got potassium and perchlorate. Well, I know I can ignore potassium because that's the conjugate, that's part of a strong base. But is that part of a strong acid? Yes, it is. Because those both get canceled out, this stays neutral. Alright, but now I'm going to change the perchlorate to chlorite, which is just ClO2 minus. Alright, I can still ignore that, but can I ignore that? No, that fits in this category like the bottom one. It's the anion of a weak acid. HClO would be a weak acid. This one's going to be slightly basic. Alright, next one, I can ignore the nitrate. If I have a nitrogen, doesn't have a lone pair on it, it's actually the cation of that weak base. So as the cation, it's going to remove some of the bases. This one's going to be slightly acidic. CH3, NH3 positive. And our last one, cesium iodide. Cesium's in group 1, so it would make a very strong base if it gets with OH, and HI is a strong acid. This is neutral. Okay, some exceptions. Let's look at something like here. So if I had just copper with something, that was actually going to make it slightly acidic, and CH3COO minus would make it slightly basic. So I have a weak acid and a weak base all in one molecule. How do we decide what's going on there? We actually have to look at the Kas in this case. Now, specifically, I want to look at the Ka for the part that's acting like the acid. And I want to look at the Kb for the part that's working as a base. So I need to get the Kb of the CH3COO minus. So we're going to do that real quick from that 1.8 there. So 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th gives me a Kb of 5.6 times 10 negative 10th. And looking at these two values, this is bigger, this one is acidic. Now the next one I did something almost, I don't know, evil, because I have the NH4 plus is going to be an acid, and the F is going to be a base, yet I gave them both to you opposite. So we have to get this as a Kb, and we have to get this as a Ka. And we can do that exact same thing. Once you get comfortable with math, you can see that you can take a shortcut here. Because I don't necessarily need to calculate this to get the answer. Oh, how about I do 1 times 10 to the negative 14th divided by that. 5.7 times 10 to the negative 10th. 0.5 times 10 to the negative 11th. The A is bigger. This is also acidic. Alright, and the last one. The K is ignorable because it's strong base, but the HSO3 could go both ways. It's either going to act like an acid or a base. I gave you the Ka version of it. We kind of just need to get the Kb of the exact same thing because it'll tell us which way that reaction is going to go. And this is another one that, if you're quick with math, you don't need to do this math either. Because that's definitely going to be a large exponent. Ka is going to be much, much larger. This one is also acidic. Okay, last little thing on our acids, it's one more definition. It's a definition of acid that doesn't involve transfer of a proton at all. It actually donates electrons. So this is a weird thing. This BF3 here actually acts almost like an H plus by itself. So we could have had an H bump into ammonia and neutralize that base and make NH4 plus. And that would definitely be an acid-base reaction. Well, this BF3 is doing the exact same thing and neutralizing that base. It's actually making a neutral molecule. And it doesn't have an H. What happens is that lone pair on the nitrogen donates itself to this Lewis acid. The Lewis acid accepts that lone pair and it makes a bond. Now it's arguable the metals are doing the same thing because the metals don't have an H. The metals actually make a solution acidic because they organize the waters around them and make one of the waters give up the H. But they just actually accept the lone pair on the oxygen and make those little temporary bonds. So, which of these, or how we identify our Lewis acids and Lewis bases? Weird thing is, we most of the time can actually get by with just looking at which one gives the electrons away. And the O minus here is definitely giving its electrons, so that is definitely the base. And even down here below, I don't have any lone pairs here to give up, so this must be the base, that must be the acid. The lone pairs get donated to the acid. Now, this one here is an interesting one. It's on how we actually see what's going on. Because SO4, when we do a Lewis structure, ends up looking like so. And if I add H's to it, put an H here and here. And then I'm going to put a bunch of lone pairs. Now, I drew it like this on purpose. I wanted you to see where this OH could come from, or the H2O could come from, and attack the SO3. So, when this was water and H2O, or an SO3, we could have drawn it like so. And we can say donating electrons to make that bond. And at the same time, it's kind of donating electrons to make that bond. Weird thing is, both species are kind of acting like the Lewis acid in that case. Which is also why that would be a horrible one to give. If I give you one of these and ask you which is acting like a Lewis acid, you're looking for something a lot more absolute. Something with absolutely no electrons to donate, so it must be the acid, or something with a lot of extra electrons being the base. Alright, next little thing we're looking at is how to actually take advantage of our weak acids and control the pH. So, a wonderful thing that we can do with all weak acids is make weird things called buffers. Now, buffers are simply just things that will hold a pH for a length of time. Reason they do that, think about in general. An HA and an A minus. The acid and the base in a pair. If they're both in solution, if I were to put a bunch of OH in here, the OH would get neutralized with some of this extra HA and would just make water and then some A minus, and the pH would be unaffected. All the extra OHs would not affect the pH at all. If I added a bunch of acid to it, it would react with the A minus and do the exact same thing. So that is our advantage of using buffers. They restrict the change based on pH. But sometimes we want to control what their pHs are. And we're going to do that with this wonderful thing. We're going to show how we could do this. So what we're going to do is look at, since we're dealing with an acidic pH, we're going to look at how an acid reacts with water to make that H3O and A minus. The difference is we're not going to have these both at 0. So I'm going to ignore this. I'm actually not even going to fully fill out this chart because we're not going to put anything there quite yet. What we want to do is the math behind it. We want this to have a pH of 4.25, so when we're all done, we want this to be 10 to the negative 4.25. And we want to get a ratio between these two that will give us that. So I want to look at what our Ka equation looks like for this. It's all for all acids. And I'm going to do a minor manipulation here. All I'm going to do is actually pull this H3O out in front of it. Now the reason I did that is because I can get this because I gave it to us. And I can get that pH because that was provided. And from that, we could actually calculate that ratio that we want between the concentrations. Alright, so let's see what that would actually look like. 6.3 times 10 to the negative fifth, and we're going to divide that by 10 to the negative 4.25. That's my ratio. It's almost a 1-to-1 ratio. Alright, now what we're going to do with that ratio is we know that we have 0.05 molar sodium benzoate, and that's my A minus. So this 1.12 equals 0.050 over whatever concentration we need of that. And it's not really asking us fully how to prepare it. I'm not even going to use this full 5 liters. I just want to know what the concentration needs to be. So I'm going to take 0.05 and divide it by that answer I just got. And I get that I would want a concentration of benzoic acid, concentration should be, what is that, 0.045? 0.045. But we're going to use that equation there to help us get to buffers, because that will always show that ratio. Alright, last thing we're going to do in this is actually try to figure out how we could predict a graph like this. Now, we're going to do this with a mix of things. I'm actually going to do this on a spreadsheet as well, so we can see the actual calculations and how they're done. But what we see on this slide is the typical titration curve you get if you were to titrate a strong acid with a weak base. We get a very rapid change near the equivalence point. It goes from very low acidic number to a very high basic number in just a few milliliters. Matter of fact, if you look at this, 39.99 has a pH of 4, 40.01 has a pH of 9. Now on this one, I'm not going to do this particular calculation on a spreadsheet. This one is actually kind of easy to do. Since we are actually able to treat all strong acids and all strong bases as just OH and H+, that's how we're going to do our ice table. And rather than a full ice table, we'd always just calculate the moles here. And whichever one's in excess is what controls the pH. If you have more H+, you're in the acidic range. If you have more OHs, you're in the basic range. You're going to subtract out whichever one is smaller. and then take the leftover and divide it by the total volume. And we're not really going to do anything with that one. That one actually, play around with it, you'll find it's actually kind of simple to do. It's just those 3 steps. The complexes one is when we have a weak acid or a weak base with a strong counterpart. So this is the curve we get if we have a weak acid with a strong base. And rather than that sharp or relatively flat and then sharp change, we get a relatively small hump and then a leveling region. So when we were talking about the buffer, that buffer region is what that means. In that area, that's where the pH is being resisted because both your acid and its conjugate base are present. Matter of fact, any calculation in that region, we can actually use that buffer calculation. But we're going to figure out how to calculate this whole thing with some formulas and such. And we're going to do that now. So I have a weak acid, HBRO, and I give you the Ka of it, and we're going to titrate it with NaOH. And my first question, very easy one by comparison to the rest, is what is the pH before any bases has been added? Well, that really is just what's the pH of a concentration of a weak acid. And we've done this a lot. Remember how we actually always simplified that ice table? But we can actually plug that in. Now, I'm actually going to write it all out. We could actually speed this process up and just use that equation I just wrote. But I'm going to write it all out just so we can see what's going on. HA plus water does go to form A minus and H3O plus. And our initial concentration is 0.2. We're going to ignore that. This is 0. This is 1.0 times 10 to the negative 7th. So our change, this is going to go down. Both these are going to go up. So equilibrium, this is 0.2 minus x. This is x. This is 1.0 times 10 to the negative 7th plus x. I'm just not going to fully solve it as I'm writing it, right? So we're going to make assumptions when we actually plug it into our calculator. So to get my x for that equation, 2.3 times 10 to the negative 8th times 0.2, and then square root. I get an H3O concentration of 6.78 times 10 negative 5th. It wants a pH, so I'm going to take the log of that. I get a pH of 4.17. Alright, next one says when HBRO or HA is equal to the A minus. Alright, that seems like a weird question, as in you might be thinking, how would I know that? Well, the interesting thing, it definitely implies they're both present. Well, if they're both in there, you're in the buffer region. So remember this buffer equation we just actually derived or figured out how we could actually write? Now, if these two are equal, wouldn't that just be 1? Yeah. So at this point, your H3O concentration equals your Ka. So its pH is the log of 2.3 times 10 to the negative 9th. And we get a pH of 8.64. So far in our graph, we have starting at about 4, and then we're in this buffer curve before we go up to our equivalence point. I'm going to put the equivalence point right there. But this 8.64 is dead middle of this buffer curve. So this is about 8.6. This is 4.17. All right, our next thing we need to do is calculate that upper point there, because that's the equivalence point. The equivalence point is when the moles of this equal the moles of that. Alright, rather than figure out what those moles are yet, I want to talk about what controls the pH at that point. Because if, let's think about it, we have a weak acid and a strong base, if they've all been totally used up, there's neither one of these anymore. So what's controlling the base, the pH, is the A- that's now built in there. So the A- now bumps into the water in there and makes a little bit of H3O plus and HA. Yeah, I don't know what I'm doing there. I'm looking at that thinking, how did I just write that? How about we do this and not create extra hydrogens? I'm donating the H there. This is OH. And we're going to have a certain concentration here, but it's essentially going to do the same type of thing as we've done before. We have a Kb where we have X and X representing our OH and our HA all over the initial concentration of the A-. Alright, but I don't know the concentration of A-. I know how many moles there are because that is just 0.2 times 0.02. That's how many moles of HBr there in there. And therefore that's how many moles of BRO are in there at the equivalence point. I have no idea what the volume is because it doesn't say anything about that. Weird thing is, we actually can calculate it. So to get the moles here to be the same, I would actually need 40 milliliters of this. So my new volume here is going to be 0.060 liters. Alright, so we got to do a couple things. I gave you the Ka, we need to get a Kb. So I'm going to do 1 times 10 to the negative 14th divided by 2.3 times 10 to the negative 9th. That'll be a Kb now. I'm going to multiply it by this stuff, so times 0.004 divided by 0.06, and then I take the square root of that. That would be my OH concentration. So this is a POH. And then to get a pH, get the difference between that and 14. So I get a pH of 10.7. Now, this next one's just kind of a weird one. It's how we calculate if there's extra OH. So rather than actually do this twice as the amount of HBr print initially, actually I can do that. Twice the amount of HBRO initially. Yeah, so it'd be 80 milliliters. Let's just do that. Let's do if it's 80 milliliters. So what we're going to do to actually solve this next one is just look at what happens initially. Those two neutralize each other. Now, we know from this calculation there's actually 0.004 moles here. If there's exactly twice the amount there, there would be 0.008 moles here. Does that make sense? Yeah. We're going to subtract out the smallest. So at this point, our OH concentration is based on those 0.004 moles of OH remaining. The only thing I have to do to get this into a concentration is divide it by the volume. Well, that would be when this is double what it currently is. So it needs to be 80, and then plus those extra 20. This is 100 milliliters. .004 divided by 0.1. That's my OH concentration. This would be a POH, and that would be the pH, 12.60. Alright, weird thing is, these 4 ways of solving it is typically not how we do a question like this. Most of the time, when you're given a question with those titration curves, you're going to be given something like this. I want you to find the pH at these 5 different points based on volumes added. Alright, the only one of these that we should be able to recognize right off the way is easy is when there's no acid added. So when there is no acid added, you are dealing with the pH of just a weak base. So we have Kb, the weak base, is always going to be the OH minus and the HB plus all over the base. And we can just plug stuff in. Our Kb, and for A, is 5.2 times 10 to the negative 4th. These are both going to be X because they were created by that stuff dissolving, and this is just 0.1. And we're just going to solve for our X and then turn that into a pH. So 5.2 times 10 to the negative 4th times 0.1, and then we take the square root of that. And we get 0.0072, and I want a pH. I'm going to take the log of that value. This is going to be the pOH because we're dealing with a base. Just add 14 to that, and I get a pH of 11.86. Alright, technically that's the only one that's going to be quick to get an answer for because it only involves the one component. The other 3, B, C, D, and E, we actually have to figure out where in the curve we are. We need to know if we're in the buffer region, at the equivalence point, or past the equivalence point. So on all these, the very first thing we're always going to do is actually figure out where we're at. So we're going to look at our acid concentration and our base that we're adding. And more importantly, I'm going to do this so we can distinguish these and say this is B. I want to look at the moles of these. And that really is because it's easier to see this with moles. So my base is always going to be 0.1 times 0.02. So this is always 0.002 moles of base initially. The H3O varies. At first, at 10 milliliters times the 0.1, this is 0.001. Alright, so we have a nice little thing. The acid's going to go away because it's the smaller of the two, leaving us some of the space. And since we still have some of that weak base in there, we now care about how much HB is in there. Originally there was none. This would have made that go up to 0.001 moles. Alright, but here's why we did this. Since these are both present, well, this is now positive 0.001. Since these are both present, we are in the buffer region. So remember our buffer equation. This is going to be slightly different because it's now a base. We're just plugging stuff in. And we can plug these in as moles because they're in the same container. But I don't need to bother in this case. They are actually exactly the same. They cancel out. Our Kb is our OH. So log of 5.2 times 10 to the negative 4th, and the difference between that and 14, this has a pH of 10.72. Alright, let's do the same initial first step for C. H3O plus is now 0.0015 because we use 15 milliliters, and the base is still the 0.002. The smaller 2 is the acid. This doesn't go to 0, so we still care about the HB plus that's being made. It's at 0, but it went up by that. So this is 0.0005, this is 0.0015, and we're still in the buffer region. So 5.2 times 10 to the negative 4th equals the OH concentration times 0.0015 all over 0.0005. Five 0.2 times 10 to the negative fourth times 0.0005 divided by 0.0015 gives us 1.7. I'm going to take the log of that to give a POH, and then I get a pH by adding that to 14. 10.24. Okay, I can look at the volume of the next one and I can see something interesting. Since it's 20, and these were both the same, D must be the equivalence point. And we can prove that by doing that exact same first step. So take the acid and the base, and initially we have 0.002 moles now, and this is also 0.002 moles. These both go to 0. Now, when they go to 0, you are at the equivalence point. So, our equation changes. We're going to have our Ka now, because we are now basing on the HB doing all the work. And our equation has the A minus and the OH. No. A minus and the H3O. All over the HA, which is our base. So, what's kind of neat, we're going to figure out our Ka. These are going to just be x's, and we're going to solve for that and calculate our pH from that. And our base concentration is these moles, 0.002 moles, divided by the current volume, 20 milliliters plus 20 milliliters, 0.040 liters. 1 times 10 to the negative 14th divided by 5.2 times 10 to the negative 4th, that's our Ka, times 0.002 divided by 0.04, and then the square root of this is our H3O concentration. Take the log of that to get the pH. pH is 6.01. Alright, last one is slightly easier because we're going to realize it's excess acid. So the acid is now 0.00205 moles because the 20.5. This is still 0.002. This goes away. Alright, the pH is going to be based on this small amount of acid that's left over. 0.00005 moles, and our volume is now 40.5 milliliters, so 0.0405 liters. 0.00005 divided by 0.0405, and then take the log of that, and we get a pH of 2.91. Alright, I know I rushed that, or went through it fast. Take your time with it, back up the video some. I plan to have some more problems like this on the practice test that are more like what we get on the practice test, so shorter. Because obviously you wouldn't be trying to do all that on a single multiple choice test question.